Hello, everyone. My name is Jonathan Anderson.
Hi, my name is Yumeng Liu, and we are third-year PhD students at Rice University working with Professor John Mellor-Crummey.
We are here to present our work on preparing for performance analysis at Exascale. Performance analysis is and will be a vital part of high-performance computing in the Exascale era. The goal of performance analysis is to identify the causes behind performance loss, which aids developers in identifying where to optimize first to improve their overall performance. Forthcoming Exascale machines pose two new challenges to performance analysis. First, performance losses may only appear at the full scale of the machine, which now contains tens of thousands of compute nodes. To identify where the loss is happening, we need to gather performance data from every application thread and GPU stream, resulting in a large volume of performance data in need of analysis. Second, providing actionable results on GPU-accelerated systems requires especially rich performance data, including most of over 130 GPU-specific performance metrics. Since many of these metrics are unique to GPU code regions, this results in very sparse performance data. Performance tools for exascale machines must handle these issues without sacrificing the quality of their analysis results. There are a number of performance tools available for GPU-based applications. Unfortunately, many contain issues that make them unsuitable for exascale machines. NVIDIA's Nsight Systems provides detailed analysis of GPU applications, but does this by processing operation traces. For large-scale or long-running applications, this results in a huge amount of data to process. Intel's VTune profiler only provides summary statistics for applications using multiple nodes. This does not provide nearly enough detail to optimize an application. In particular, there is no attribution back to the original source. ARM's map is designed for very large scales, but does this by reducing their data collection to a finite number of samples per thread. By default, only 1,000 samples are kept per thread. This is only suitable for coarse-grained performance analysis, and is insufficient for application development and optimization. Tau, Scholastica, and other tools based on the ScoreP measurement framework are missing key features required at scale. First, the cube data format used by ScoreP does not exploit all of the available sparsity in these performance data. This will inevitably result in obstructively large data at scale. Second, many of these tools are limited to a single compute node, or operate as part of a graphical interface. This severely limits their available compute resources and analysis time and makes them unable to scale for large data. Third, one of the few tools that can use multiple nodes, Scholastica's Scout, must run at a scale identical to the application. For extreme scale applications, this will expend a huge compute cost just on analyzing performance data. On top of all these issues, none of the tools mentioned so far provide full calling context within GPU code. In fact, only Nsight provides any detail within a GPU kernel launch. We are aware of applications with hundreds of thousands of lines of code in a single kernel. Sub-kernel performance results are absolutely required for developing these codes. In our work, we focus on preparing HPC Toolkit for GPU-accelerated exascale systems. This slide shows one of our previous success stories using HPC Toolkit to optimize Pele-C, a GPU-based hydrodynamics code. The left side shows part of a hybrid CPU-GPU calling context tree, displaying both the host side calls leading up to a kernel launch and the functions and loops within the kernel. From the performance metrics on the right, we can pick out that 9% of all GPU stalled cycles in the entire program were spent on the selected line, which is outside the loop shown in the top pane. Of these trailing stalls, we can also determine that the vast majority of them are memory stalls. This indicates that this kernel, in particular this line of code, is wasting significant time waiting for memory. Why is this happening? By inspecting the code, we can see that a U data pointer is being passed through the lambda capture. Since this structure is allocated on the host, every access through this pointer is going through unified memory. If we instead pass the reference values as scalars through the lambda capture, we will be using constant memory, which is much faster and closer to the device. We recommended this change to the development team, and they were able to obtain a 4% speedup in practice. This short example demonstrates the need for rich performance data on GPUs. Without line-level information or without memory stalls metrics, this optimization would be much more difficult to hunt down. The tool we develop, HPC Toolkit, is a scalable performance tool that provides this level of rich performance data. Our tool consists of 4 simple steps. First, HPC Run profiles every thread and GPU stream in the application, using sampling to minimize overhead and support large-scale executions. HPC Struct then extracts program structure information from optimized CPU and GPU binaries, identifying functions, inline function calls, loops, and source lines. HPC Prof attributes performance gathered at runtime with program structure, resulting in a single unified performance database. HPC Viewer then allows you to browse this database using a graphical interface, allowing you to identify performance losses and hotspots with just a few clicks. To address the challenges posed by exascale systems, our work focuses on improving the scalability of HPC Toolkit. In particular, we focus on improving the performance of HPC Prof, which must analyze the increased volume of performance data. We also improve the scalability of the formats we use to store performance data, namely the measurement profiles gathered for each thread and GPU stream, and the resulting performance database. Our approach to performance analysis on large and exascale systems is as follows. First, we exploit the natural sparsity present in large-scale performance data. This significantly reduces the storage requirements and efficiently uses the I/O available on these systems. Second, we use multithreading to process the performance data. This reduces our memory footprint and communication costs compared to MPI-based parallelism, and efficiently uses all available compute on each node. In the remainder of this presentation, we will describe these approaches and then present some of the improvements we obtained in practice in our experiments. In general, our increased efficiency has allowed us to process performance data from thousands of compute nodes using less than 10 in only a few minutes.
Now, let's talk about the first approach. How do we use the natural sparsity present in the large-scale performance data to reduce the storage requirements? We first focus on the first part, natural sparsity. Why do we have them? There are several factors actually contribute to it. First, threads all have different roles. They will have zeros for contexts that only appear in other threads. For example, MPI helper threads, OpenMP worker threads, and GPU streams. Also, metric costs accumulate in expensive leaf functions. So for the distance callers, like the high-level functions, they often have no exclusive metrics. And then many metrics apply only to certain instructions or code regions. For example, the TLB miss, it only applies to memory access. And for the GPU cycles, it only applies to GPU code. And then some metrics also only apply to very specific contexts. For kernel launch parameters, it only applies to GPU kernels. For data motion volume, it only applies to GPU copies. So all of these factors I mentioned, they all contribute to sparsity. Now, let's talk about exactly what kind of performance data we're recording. We measure values for each metric and calling context for every application thread or GPU stream. Basically, for each value, we need to know which metric it represents, which calling context it relates to, and which thread or GPU stream it belongs to. And due to the factors I mentioned previously, they are very sparse. So we can think it as a three-dimensional sparse tensor, and basically as what we show on the right. So in practice, how sparse they are. We did a bunch of experiments on both CPU-based code and GPU-accelerated code. For CPU ones, we have AMG 2013. For GPU ones, we have LAMPS and Pele-C. For the AMG, the difference between the first one and the second one is for the first one, we only used one CPU metric. And for the second one, we used 7 CPU metrics. And the upper half of the table is about measurement data, which is the input for HPC Prof. And the lower half is analysis results, which is the output for HPC Prof. Let's first talk about measurement data. So with 7 CPU metrics, roughly 23% of the contexts have metric values and 21% of the values for contexts are non-zeros. So only 23% actually have some values. And in those 23%, only 21% of them are actually non-zeros. And then for GPU metrics, 16% of the contexts have metrics values and 2% of the values for those contexts are non-zeros, which means we only have roughly 0.32% of the data, of the whole data, are non-zeros. Roughly 99% of the values are all zeros. And then for analysis results, the situation is even worse. In all of our experiments, at most 2.3% of the contexts have metric values and 1.4% of the values for those contexts are non-zeros. As we can see, the degree of sparsity is huge here, it's very high. Let's move to the second part of this approach. how do we actually use this sparsity to reduce storage requirements? Let's first talk about the measurement data. For the measurement data, we record a performance profile for each thread and each GPU stream. So there are many files. For each profile file, we have values for metrics associated with calling contexts. As what we show on the left, basically for each profile file, we can think it as a 2D matrix. It's a matrix, it's sparse. Then we thought about the compressed sparse row format. And our approach was actually inspired by it, which is shown on the right. We have two vectors. The first vector records the non-zero values and their metric IDs. The second vector records the non-empty calling context and the starting index. The non-empty calling context means the calling context that has at least one non-zero value. And the starting index here means the starting position of the MV pairs of this context in the MV vector, the first vector. As you may notice, we actually exploited the sparsity in both metric dimension and context dimension. For metrics, we only recorded those non-zero values in the first vector. And for context, we only recorded non-empty context in the second vector. For example, context 2 here has all zeros. There's no non-zero value. So in the second vector, we're not recording it. And also with binary search, we can ensure logarithmic access time to all the values. Unlike measurement data, for analysis results, we put all the data for all profiles, all contexts, all metrics, everything in one place. However, we don't just have one file, we actually have two files, and each of them contains all the data. The only difference between them is the ordering. Why? Because we have two use cases when we inspect our analysis results. On the left-hand side, we have profile major sparse, or PMS. On the right-hand side, we have context major sparse, or CMS. For PMS, data for each profile is contiguous. For CMS, data for each context is contiguous. So with PMS, it will be much easier for us to check the whole performance of one thread or one GPU stream. And with CMS, it will be really good for us to check the metrics for one single context across all threads. For example, it will be ideal for us to use it to check loading balance. In terms of the format here, now we put three dimensions together. So we do need the third vector. And we use a dense vector here to ensure constant time to access the values of one profile in PMS or one context in CMS. And inside each plane is exactly like the format in measurement data. Due to the time limit here, I'll leave the details in the paper. To summarize, we implemented a set of sparse performance data formats, and we exploited the natural sparsity of the performance data from two dimensions to reduce the storage requirements. But still, we retain efficient and low latency access to values properties.
Our second approach is to use multithreading during analysis. This allows us to efficiently use all available compute at analysis time, allowing us to scale to exascale performance data. We use a novel parallel approach we call streaming aggregation, which breaks the problem of performance analysis down into three classes of operations. We number these based on the data dependencies between the operations. Class 2 operations may depend on Class 1 operations, and Class 3 operations may depend on operations in Classes 2 or 1. To achieve parallelism, we add restrictions on these operations that we will exploit for high performance. The simplest restrictions are on Class 2 operations, which must operate independently on each performance profile. An example of this is calculating inclusive cost metrics for each application thread and GPU stream. As shown in the figure on the right, these operations run in parallel with no notable communication. Each thread independently reads in performance data and writes out per profile analysis results with little to no synchronization. This streaming approach limits the memory footprint used during analysis. Only profiles being actively processed are loaded into memory. This allows a single process to analyze as many profiles as needed without exceeding the memory on a single compute node, improving our scalability. Of course, performance analysis with this restriction would not be particularly useful. Operations which act across multiple profiles are in Classes 1 and 3, with stricter restrictions. Class 1 operations are formally associative, commutative, and idempotent, and are required for per-profile output. An example of this would be correlating calling contexts across performance profiles, such that there's only one calling context node for every unique call path. These must be correlated early, so context IDs in the output are consistent across profiles. Class 3 operations are formally associative and commutative. These aggregate the per-profile analysis results. An example would be generating summary statistics for the entire execution, which is similar to a sum of the performance measured from each application thread. Both Class 1 and 3 operations are implemented by updating a series of shared concurrent data structures in parallel. The restrictions on both Class 1 and 3 operations allow them to be reordered without affecting the result, so we run them when convenient. Class 1 operations run on demand as required by Class 2 operations, while Class 3 operations run once a profile has completed processing. This approach does not require large serialization like phases or barriers. Instead, all synchronization is fine-grained and data-centric, minimizing the total serialization. This allows our approach to outperform the conventional reduction-based approach to aggregation, which our paper also demonstrates in practice using a micro-benchmark. Multithreading allows us to efficiently use the entirety of a compute node. However, this alone does not make us scalable. To scale past a single node, we extend streaming aggregation in a hybrid approach. We use streaming aggregation within each node and MPI to communicate across nodes. Our restrictions ensure that only operations in classes 1 and 3 require communication between compute nodes. For these classes, we add an MPI reduction to merge results across nodes, one for each class, as shown in the figure on the right. Class 2 operations are independent and do not need communication, so these are distributed evenly across the compute nodes. Each node performs its own I/O, thus using more of the available bandwidth in the underlying distributed file system. In total, this hybrid approach allows for scalable and highly parallel performance analysis. To show the benefits of our approach in practice, we implemented our hybrid approach in an improved version of HPC Prof. This slide shows an execution trace of it running on 8 compute nodes. White parts of the trace indicate idleness, while flecks of color indicate activity. Regions are labeled with the rough phases from the previous figure. The center red region is dominated by our multi-threaded streaming aggregation approach. Here we can see the dense parallelism afforded by this approach. In comparison, the green and blue regions to the left and right are dominated by MPI reductions. Here we can see the large idleness incurred by these large synchronizations. This demonstrates at a glance the benefits of using a hybrid approach. Pure MPI parallelism would likely be dominated by the idleness. The small purple region at the end of the trace marks an out-of-court transpose for our context major sparse format. We use an efficient algorithm here to ensure this phase does not become a performance bottleneck. We compared the performance of our improved HPC Prof against the original, analyzing data gathered from Pele-C, a GPU-based hydrodynamics code. The experiments shown here analyze data from Pele-C running on 500 or 2000 GPUs, respectively, and used 63 threads per node during analysis. Overall, our improved HPC Prof runs 30 to 80 times faster using the same compute resources as the original. The smaller memory footprint of streaming aggregation is crucial to this speedup. The original HPC Prof exceeded the system memory per node, so for these experiments we had to use 16 times as many compute nodes to successfully process the same inputs. Another critical benefit to our improved HPC Prof is that we only use a fraction of the compute resources used by the application. In these experiments, we ran Pele-C on up to a third of Perlmutter, 500 nodes, while for analysis we only needed 8 or even a single compute node. This scaling allows us to analyze applications running at full scale without incurring an unreasonable analysis overhead. Finally, in our experiments, our improved HPC Prof generated detailed analysis results in only 1 or 2 minutes, compared to the original, which took at least half an hour to generate similar results. These improvements are not limited to GPU codes. Our paper presents additional experiments based on AMG, a CPU-only multi-grid solver. Our improvements do not stop at analysis time. Our new formats also significantly reduce the space requirements for these experiments. By exploiting sparsity, we compressed our measurements by up to 10 times and compressed our analysis results by up to 1,200 times, counting execution traces in both sparse formats. In particular, our formats are able to provide detailed analysis results in gigabytes, not in terabytes like the original HPC Toolkit. This is crucial to scalable performance analysis. As applications get larger, these sizes will grow linearly. Tens to hundreds of terabytes will quickly exceed the storage quotas available on most, if not all, supercomputers. Our paper includes results from additional experiments, as well as the comparison against Scholastic's Scout tool, which is based on the SCORP measurement framework.
Let's conclude. Less is more. The efficient use of compute resources is the key for us to succeed in the exascale era, which means we need to exploit sparsity to reduce storage and I/O, or we need to exploit multi-threading to efficiently use each node's cores and threads. We also need to exploit distributed memory parallelism for scalability. To be more specific, we created a set of novel sparse formats for performance measurements and analysis results. With that, we achieved up to 1,254 times compression in analysis results for our experiments. We also created a novel, highly parallel approach, streaming aggregation, to performance analysis. With that, we can run the analysis and get the results for large-scale executions in just a few minutes. All in all, we are better prepared for performance analysis at exascale. And I have a good news, the improvements are actually actively being integrated into HPC Toolkit, which means it will become widely available in a future release. In terms of the future work, we still want to improve the performance and the scalability of I/O. Because for the measurement data side, we still need to write many small profile files. And writing those files is problematic for classic distributed file systems. And also, there are a lot of new technologies, especially I/O technologies like DAOs. We should try to exploit them to help us improve the performance and scalability of I/O. Second, we also want to improve performance and scalability of distributed memory approach. Currently, the internode reductions still involve significant idleness. We'd like to thank our various sponsors for supporting our research, and thank you all for listening. If you have any questions, please feel free to join us in the Q&A session. See you at ICS 22.